Hi. So um, today we'll go through the PCA. Yesterday we started with PCM. We were getting in detail. We looked at standardization. That is the X features values are usually continuous. So such continuous values could be ranging from a wide range, right? Right, like be something like minus 100,000 to plus 4 million, something like that, like big numbers, right? Could be varying, and then dealing with such variable numbers. And for example, something measured in centimeters, right? It will be big, huge. But whereas the same thing, someone, some other dimension, which is actually in like currency, something like that, it's relatively small, right? So what happens is the numbers are not relative with respect to size. Um, Size in the sense multiples. One could be in hundred thousands, another could be in 0.2, 0.4, 0.5, something like that, right? So to bring them to a similar scale and also to get an even distribution. So distribution, as per what we studied yesterday, distribution is the way we look at it. If we take a set of numbers, take a mean of that particular number, like set of numbers like this, if you put it them in a straight line, and you take a mean of that numbers somewhere in between. Distribution is the way we look at it on how much they are spread from the mean kind of stuff, right? That gives us like how these numbers are, how far are these numbers from this particular mean. Basically, that difference from the mean is called variance, and basing on variance, we difference alone, not difference alone. Sum of squares mean is variance. Square root of sum of squares mean of differences between the mean and the point is standard deviation. How it is a significant variance and standard deviation are a mathematical calculation, but logically on um, how do we, what is the purpose of calculating variance and standard deviation? I don't see a logical explanation, but those are one metrics of a series of numbers. Like you have a set of numbers, you can calculate mean. You try to see, instead of looking at all the numbers, the mean will give you what's on sort of a mid value, not even mid value, what sort of a value that is there, where these numbers are distributed across those numbers. Similarly, variance gives how much these numbers are um, spread from the mean. Um, Similarly, standard deviation will actually, standard deviation will give you more accurate how much they are spread on the mean, because variance is a mean of the squares of these differences, variance. um, but standard deviation being square root is much closer to the actual values on y minus y mean kind of stuff, and this varies with the points, right? There are some outliers, then the variance are the distance between mean and these points will be higher. Something will be very close, will be smaller. So considering all those differences between the mean and the actual points, standard deviation is calculated as an average of the differences between the mean and the other points. So that will give you a rough idea on how much the distribution is. That's about variance and standard deviation. So first step that we looked at is standard. I couldn't find that block for some reason. I think this is the block, is it? Okay, I'm not sharing the screen back. Okay, let me share the screen. Yeah, I think this is the block that we're following. It had steps, no? Yeah. So component analysis. Yes, this is the one. Standardization. Step one standardization is value minus mean by standard deviation. We calculated on how it is. So what happens if we do this is value minus mean. Once you do it, the mean of these numbers will become zero. You remember we asked ChatGPT to calculate and it was not calculating properly because of rounding off the numbers and stuff. So value minus mean by standard deviation. Standard deviation gives us the average distance of the points from mean is what we discussed, right? So what happens each value if it is divided by that average distance, now what happens if you calculate standard deviation, the standard deviation of these numbers, that's a good point. Standard deviation of these new numbers that is there from highest values above the mean of the result values and their standard stand, standard values obtained previously. Mean he calculated and said 0.02 something. Oh my god, this guy is in this cross validation mode, so he's making sure. So what happens? Mean becomes zero, then square root of sum of squares by n. Previously standard deviation is 11. That means the distribution is 11. Now it has been brought down to 3.672. By dividing the standard deviation, we are actually bringing it much closer to the mean. That's the whole point. Besides, the numbers are, so the mean is like this. We are shifting the mean to zero, and these numbers we are moving them relatively by doing a minus mean. Something like the number mean is here, and the number is here, like 10. Now mean is 4, 10. We are moving mean from 4 to 0, and 10 minus 4, 6. We are moving it closer here. So, and previously it is 4, and then imagine standard deviation, average standard deviation across all the numbers. Not average standard deviation, average distance from mean we are considering as the input for standard deviation, right? So that average we're taking and dividing so that relatively all the numbers will be sized down, divided by standard deviation will bring it here somewhere, right? Like 0 to it became 4. Now, um, what did I say? 4 to 4 to 6, is it? If it is 4 to 6, 4 being moved to 0, it will become 0 to 2. 2 again will be divided by standard deviation. Let's imagine it's 10 deviation. Then 2 by 10 will become 0.2. So it will come very close to 0. So the distance from the mean, it will actually be reduced. That's the whole objective. Okay. Standard deviation, previous numbers, if you remember, it is it's 11. From mean 36.5, we brought it to 0, and standard deviation from 11, we brought it to 3.600. That means the spread of the numbers, we've reduced the spread of the numbers related to mean. So we're not making it same for all the features. All the features, the standard deviation will be different. But what we're doing is, instead of having a high range of numbers, we are reducing it to, we are minimizing it. Okay. Then going back to the blog, standard deviation is done. Standardization is done, or standardization is done using this formula. Covariance matrix computation. This I tried to see. So covariance of x comma y is nothing but x um, sigma x sigma x I equal to 1 to n, assuming x and y are belonging to same data set, will have equal number of values n, right? So it will be x minus x mean, xi minus x mean into yi minus y mean by n. Why do we multiply xi minus x mean and yi minus y mean? I don't know. And why do we divide it? I mean, we're calculating a mean of those that particular multiples. So we're taking the differences from mean of all the points of x and y. We are multiplying them with each other, the distance between the mean and the actual points. And so the distribution of x with respect to its mean and distribution of y to its mean, those values are being considered, and those values are being multiplied, and then we're taking an average of those numbers, and that's what we are representing as covariance. Compute the oh, this is how the covariance will work, is what they were saying. So covariance, sum of or mean of multiplication of differences from mean. If you look at it, uh, from the mean, if both of them, oh yeah, both of them are positive and both of them are negative at the same time, possibly with few exceptions, then mean of the product of the distances between mean and this number and mean and y number will be positive, because negative negative multiplication is positive, positive positive is positive, covariance will become positive. Whereas if they are going opposite, then what will happen? From mean, one will be going towards positive direction, other one will be going a negative direction. So positive, negative, negative, positive. So both will become minus most of the scenarios. Mean of those numbers will become negative. That means most of the cases they are going in opposite directions. But there's a possibility that half of them are going in same direction and half of them are not going in same direction. Then also the possibility, and also basing on the ranges, let's say the y minus yi is very small, the distribution from 0 it's just 0 to 1 values, whereas x is from minus 10 to 10 for some reason, then the multiplication will actually, even after standard deviation, let's say still it is minus 10 to 10 range of the values, then x will dominate in the covariance. But actually the value doesn't matter, right? The sign matters. Sign matters, but what happens is the negative values and positive values of x will start influencing the overall value. One big negative value of x can take away all the positive values of y and still make it negative. So the calculation is of covariance is still biased for sure. Okay, then anyways, that's the maximum amount of time somebody can build on covariance. But okay, let me still, I want to go through a little bit more covariation and covariance as a two random numbers. So in my here we define the covariance of x and y. Do some information about how x and y are statistically related. That is part of the application of covariance. Okay. X minus x mean, y minus y mean by slash and he has removed. Okay, fine. What does he mean by E? Okay. Maybe E itself means mean. Okay. Hmm? E of xy. Yeah, y of x, E of y. E of xy minus E of x into E of y. Mean of the product minus mean of x and mean of y. That's what he's trying to say. Intuitively, the covariance between so it indicates how the values of x and y move related to each other. If large values of x tend to happen with large values of y, then x minus e x y minus y is positive on average. In this case, covariance is positive, and we say x and y are positively correlated. On the other hand, and if x tends to be small, in this case the covariance is negative, and we say negatively correlated. So of x comma y is equal to variable of x, x comma x. If x and y are independent, then equal to 0. How can it be 0? I don't know. Covariance of x comma y is equal to covariance of y comma x. A into covariance of x comma y. The over results can be proven directly from the definition of covariance, for example, if x. X1 y1 plus x2 y2 plus on xn yn by n minus x1 plus x2 plus x3 plus so on xn into y1 plus y2 plus y3 by n. How can both of them will become same, man? I don't know. That's okay. That's all math. The correlation coefficient denoted by oh, some character. I don't even know what character is obtained by normalizing the covariance. Normalizing the covariance. In particular, we define the correlation coefficient of two random value variables x and y as the covariance of standard versions of x and y. Define the standardized versions of x and y as standard deviation is never negative. So dividing by standard deviation of x and the standard deviation of y is nothing but square root of rx by ry. So, y. So same looks like same value, but just dividing it. Thing about the correlation coefficient is that it is always between -1 and 1. Mm, this is an immediate result of Cauchy's class inequality that is discussed in section 6.2.4. One way to go -1 is to use for any real numbers, product of the numbers, alpha beta is less than or equal to, so 2 alpha beta, alpha square plus beta square minus 2 alpha beta is greater than or equal to 0. That is because alpha minus beta is whole square. It is always greater than or equal to 0. Makes sense. Then alpha beta is less than or equal to alpha square plus beta square by 2. Okay, makes sense. I can below here is given. The equality holds only if alpha equal to beta. Covariance is no, correlation coefficient is covariance divided by standard deviation of both, and standard deviation of covariance is sum of product of the differences by n. Standard deviation is square root of sum of squares of differences by n, but they are square n become n cancelled. That is sum of products of x, y, and square root of sum of squares of x minus xi. Oh, okay. What he's trying to say is square root of square number, sum of squares. Um, yeah, as long as it is square root of x, but one is it's positive, and it is always squares is always greater than sum of squares is always greater than product of squares. Oh, here itself. So alpha square plus beta square by alpha beta, or alpha beta by alpha square beta square, it is less than or equal to 1 by 2. That means but buddy, there is a square root on top of it. Okay, let's see. uncorrelated. There's no relation between x and comma greater than 0. They're partially correlated. And 0 negatively correlated. Okay. This is too much of Gyan for day. Enough. Let's go back to this. Okay, next step of covariance is step 1 standardization. Step 2 calculation of covariance. Compute the eigenvectors and eigenvalues of the covariance matrix to identify the principal components. Okay. That is our linear algebra concepts that we need to compute from that. If this vector and eigenvalues which are so basing on covariance, you calculate eigenvectors and eigenvalues. What eigenvectors is, eigenvalues is, we'll look into it. But what you do is you calculate by ranking eigenvectors in order of their eigenvalues. You order by eigenvalues, highest to lowest. You get the principal components in order of significance. Okay. Okay. Eigen value, which means that the A component PC1 is B1. After having the principal components, to compute the percentage of variance accounted for by each component, you divide the eigenvalue of each component. Aim is to use the feature. Oh, virtual common analysis looks very complicated, but okay, stepping backwards. So when there is something called agent vectors and agent values. Let's watch a video, man. Maybe. So it's complicated. That's the summary. Eigen vectors, eigenvalues, and all that stuff. End of the day, what he's doing is calculating all that. AB, he is deriving AB, and AB, what he is doing, A into x minus x mean plus B into y minus y mean. AB are values that he has derived as the eigenvector, and basing on that, basing on these features, he's calculating the first component analysis. Similarly, if we um, on the first eigenvector. And if we take second eigenvector, which is calculated basing on the second eigenvalue, lambda 2, then using that second eigenvector, we multiply and derive the second principal component. So, getting into the detail on what this principal component is and stuff, I didn't understand this graph he has drawn and stuff, which goes in positive direction, negative direction, projecting the values and stuff. That is not clear, but principal component analysis is in turn But principal component analysis by looking at a into x minus x mean plus b into y minus y mean kind of stuff, where a b are calculated by some math, eigenvalues, eigenvectors, whatever, um, that being considered. So it's a combination of multiple features together. Um, it's equation. Principal component analysis is actually an equation which actually is derived from the remaining features, which we believe is the right thing to do, or on reducing the feature dimension kind of stuff. So I mean, I'm assuming if there is x, y, and z, then it will become a into x minus x mean plus b into y minus y mean plus c into z minus z mean. Um, and that will give us the first principle. Instead of ABC, if we use lambda 2, it will become DEF. Then it will become D into x minus x mean plus E into y minus y mean plus F into z minus z mean will become the second principal component analysis feature. Like that, we found certain features, and on these features, we do the modeling and take it forward. And these features calculated basing on multiple features as a combination is effective, is what we were saying. Got it. Okay. So with this, we'll stop the principal component analysis. Not 100% satisfied and complete understanding, but it is definitely complicated. At times, we need to step back and say, "Boss, this is not your cup of tea." So we should agree the defeat. But yeah, so standardized values are being taken, and then the covariance is being taken. Post covariance, they are calculating the eigen values, and then eigenvalues, they are calculating eigenvectors. From eigenvectors, they're calculating the principal component by multiplying the eigenvector with the standardized eigenvectors transpose into standardized values transpose, and that will give us certain principal components. Um, so you can use different eigenvectors, multiply the to derive multiple features, and this set of new features that we derive will be used as principal components one, two, three, and four kind of stuff. Mm, lambda 1, lambda eigenvalue 1 and eigenvalue 2, eigenvalue 3, how are they making sure that they are giving us the best principal component 1, 1, 2, and 3 and stuff. I didn't understand that concept as well. There are gaps in the understanding, but I think we should live with it. Or maybe if we read somebody, we should ask them. Before we close off for today, let's ask ChatGPT what are other dimension reduction techniques beside PCA. Besides PCA, there are several other dimension reduction techniques commonly used in machine learning and data analysis. Some of these techniques include linear discriminant analysis. People would have wrote so many papers on this because it's a very important concept, especially dealing with multiple features and stuff. They would definitely get into this question on how do I reduce this thing, right? Linear discriminant analysis is a supervised dimension reduction technique that maximizes the separability between classes while reducing the dimensionality of the data. T distributed stochastic neighbor embedding is a nonlinear dimensional reduction technique commonly used for visualizing high dimension data in low dimension space. Together, okay. Autoencoders. Autoencoders are neural network architecture used for unsupervised learning that learn to encode high dimensional input data into low dimensional latent space and, and then decode it back to the original dimensions. By training the autoencoder to minimize the reconstruction error, meaningful representation of the data can be learned. Isometric mapping. Isomap is a nonlinear dimensional reduction technique that seeks to preserve the shortest path distances between mapping high dimensional data onto a lower dimensional manifold. It is particularly useful for applying success. Locally linear embedding. LLE is a nonlinear dimensional reduction technique that preserves the local relationship between data points. Low dimensional reduction of data point. It is expressed as linear combination of its nearest neighbors. Okay. Sparse coding is a technique. But the sparse representation of data by finding a set of basic functions. Dimensional reduction by projecting data into an independent component analysis. Blend source operation techniques that aims at operating multivariate. Used for dimensional reduction by identifying statistical independent components in the data. It's like x1, x2, x3, x4 are there, x1 plus x2, x2 plus x3, x3 plus x4, something like that. The few of the dimensional reduction techniques from sites PCA, the choice of technique depends on the characteristics of the data and the design properties and the specific goals of the analysis. Okay. So that means overall, in summary, there are a lot of dimensional reduction techniques, and we should people understanding those techniques and implementing depends on the data that they have and stuff. They should make a choice, and once you get deep into it, you should have an understanding of all these dimensional reduction because you don't know which one needs to be used at which place, and you should use them accordingly. Okay, for now we will wind up with PCA, but we'll try to cover them at some point after. But this is pending thing, like deeper understanding of PCA, which is widely used, and next to it is these 7 other dimensional reduction techniques and how people make a choice on which dimensional reduction to be used. Instead of using PC all the time, using all the data, we should actually pick up a specific technique, dimensional reduction technique, and then use this particular technique. That's, I think, the way forward. Cool. We'll think through and see what we need to. Data exploratory analysis is what we will cover tomorrow. To see what are the other things that could be done as part of data exploratory analysis before taking forward and building the model kind of stuff. Okay. I think PCA does majority part of the data exploratory analysis that needs to be done, but with respect to features, data, standardization, but we'll look at it. Right. Okay, that's it for today. Thanks, guys. Bye.